Welcome to the PowerPoint presentation relating to the course 6325 State Space Control Systems. My name is Prasanna Kumar Reddy Gade and the topic of presentation is matrix algebra and linear equations. Let us have a quick glance of the contents that we are going to discuss in this presentation. Firstly, we are going to go through some introduction to matrix algebra and linear equations. After that, we'll see the relationship between matrix algebra and linear equations. After that, we'll go through the applications of matrix algebra, and finally we'll see some miscellaneous applications. Now, introduction to matrices. What is a matrix? A matrix is a rectangular array of numbers, symbols, and expressions arranged in rows and columns. So we have this matrix whose order is m by n. By this we mean that m denotes number of rows and n denotes number of columns. So this matrix is said to have m rows and n columns. This is the generalized form of a matrix. Similarly, we can see that we have the MATLAB representation of a 3 by 3 matrix. As you can see, there are 3 rows and exactly 3 columns in this matrix. Similarly, we have a MATLAB representation of a 3 by 3 diagonal matrix. Diagonal matrix is a special kind of matrix in which all the diagonal elements are non-zeros and all the non-diagonal elements are zeros. What is matrix algebra? Matrix algebra is a means of making calculations upon matrices, that is, arrays of numbers or data. Matrix algebra makes mathematical expressions and computations easier. It also allows you to get rid of difficult notations, concentrate on the concepts involved, and understand where your results come from. So examples of matrix algebra is matrix addition, matrix subtraction, matrix multiplication, etc. Here we have matrix addition. Let us go through this. So we have two matrices, matrix A and matrix B. We have the elements in matrix A and elements in matrix B. We just need to add these two matrices. So what we do is we add the first element, that is the first element in the first row and first column of matrix A with the element in first row and first column of matrix B. Similarly, we end up adding all the elements which are in the same identical position in each matrices, and we get these resultant matrices like this. Again, what is matrix multiplication? We have two matrices, matrix A and matrix B. We need to perform matrix multiplication on this. So A multiplied by B is something like this. So first we start with the first row of matrix A, and we start with the first column of matrix B, and we perform calculation on this. So we get A11 into B11 plus A12 into B21. So this would be the first element in the matrix AB. Similarly, the second element would be A21 into B12 into A22 into B22. So here we have this matrix. Similarly, we can get all the elements that we desire of this matrix. Now, it is important to note that in general in matrix multiplication, A cross B is not equal to B cross A. So the order in which we multiply is extremely important. If we have two matrices, we can only follow a certain order. We cannot change the order. If we change the order, the resultant matrix would end up getting changed. Two matrices may be added or subtracted only if they have the same dimensions. That is, they must have the same number of rows and columns. This is very important. And in order to multiply two matrices, the condition is that the number of columns in A must equal the number of rows. Now, what is transpose of a matrix? The transpose of a matrix is a new matrix that is formed by interchanging the rows and columns. Let's say we have a matrix denoted by A, then its transpose will be denoted by A transpose or with this symbol. So let us say we have this matrix A, we need to find its transpose. So all we do is just interchanging the rows and interchanging the columns, and we get the resultant matrix. What is a symmetric matrix? A matrix A is said to be symmetric if A is equal to A transpose. So if we have a matrix A and we perform transpose on it, and we find that the resultant matrix is again the same matrix, then we can say that it's a symmetric matrix. Determinant of matrix is denoted by det of A or with this symbol which looks like modulus. So only square matrices are said to have determinants. So if we have this 2 by 2 matrix A whose elements are like this, then determinant of A can be followed like this. It can be performed like this. Properties of determinants. Determinants have several mathematical properties which are useful in matrix manipulations. So the first property is determinant of A is always equal to the determinant of A transpose. And the second property is if row or column of A is equal to 0, if the whole row or whole column is equal to zeros, then the determinant is definitely going to be 0. If every row in a if every value in a row or column is multiplied by k, then determinant of A would also be multiplied by k. So it would be k times determinant of A. If two rows or two columns are interchanged in the sign but not the value, the determinant changes. If a matrix has two identical rows or columns, then determinant of A equal to 0. If two rows or columns are linear combination of each other, then determinant of A equal to 0. Adjoint of a matrix. In linear algebra, the adjugate, classical adjoint, or adjunct of a square matrix is the transpose of its cofactor matrix. So what is a cofactor matrix? We have this matrix, as you can see. We have elements A, B, C, D, E, F in the second row and G, H, I in the third row. If we want to find the cofactor of each element, we just need to perform something like this. So as you can see, we are trying to perform the cofactor of element A. So element A is in the first row and first column. So if you can just ignore the first row and first column and see the rest of the matrix, we have elements E, F and H, I. We need to multiply E with I and H with F and just subtract EI, HF from EI. So this is how it looks. So this is the process in which we try to find the cofactor of each and every element. So once we get the cofactors of each and every element, we just transpose the whole matrix, and the resultant matrix is an adjoint of a matrix. Now, one thing is that we should look at is each determinant in cofactor matrix has a cofactor sign determined by the location of the element that was eliminated. Sign is defined as follows. So sign is definitely important. We need to take care of the sign. So the way sign works is every time the element at which we are looking at the sign, it should be -1 power I plus j. So I is the number of that column, number of that row, sorry, and j is the number of column. I is the position of row and j is the position of column. Inverse of matrix. In matrix algebra, an n by n square matrix is said to be invertible if and only if there exists an n by n square matrix B such that A multiplied by B is equal to B multiplied by A is equal to inverse matrix. Let's say we have a matrix A, then inverse of matrix can be found by inverse of matrix A is equal to adjoint of A by determinant of A. So as we have already discussed, adjoint of a matrix is nothing but the transpose of its cofactor matrix, and the determinant of A can be found, we have also discussed the determinant of A. So inverse of a matrix A is equal to adjoint of a matrix by the determinant of the same matrix. The inverse is analogous to a reciprocal. A matrix which has an inverse is non-singular. A matrix which does not have an inverse is singular. An inverse exists only if determinant of A is not equal to 0. So if the determinant is equal to 0, then inverse does not exist. Linear equations. A linear equation is a type of equation that can be written in the form a1x1 plus b a2x2 plus and so on till an xn plus b equal to 0. In other words, it is an equation between two variables, or it can be equation between 3 or 4 variables depending upon the number of planes. If you have two planes, it would certainly have two variables, but if you have three planes, if we are seeing the system in a three dimensions, then we have three variables. Here is the example of a linear equations plotted on a graph. This is actually a two-dimensional plane, so we have only two variables y and x. Similarly, we can see we have a three-dimensional system, so the system of linear equations can be represented as follows. These are the set of linear equations. Now, what exactly are the system of linear equations, and what is the relationship between system of linear equations and matrices? Any set of m linear equations in the variables x1, x2, xn can be represented by the compact matrix equation Ax equal to b. So any set of linear equations, no matter how many linear equations are there, we can always represent them in the form of matrices. We have this example. You can see, so let us think about a system of linear equations. We have the first linear equation, the second linear equation, the third linear equation. Now, if we want to form matrix out of it, we just need to take the coefficients of each in front of each variable and put them under a matrix like this. So from the first linear equation, we have x plus y plus z. We have the coefficients as 1, 1 and 1. So we've just put it under a matrix in the first row. Similarly, in the second matrix, the coefficient of x is 0, so you put 0 over here, and the coefficient of y and z are 2 and 5 respectively, so put 2 and 5 in the second row. Similarly, in the third row, we have 2, 5, and minus 1. And again, multiplying this with a 3 by 1 matrix of the variables x, y, and z, and we can put the resultant again in the 3 by 1 matrix like this. So this is the again one more example we have. We can see we have a matrix. We already have a matrix. We already have the numbers in the form of a matrix. Now it can be seen from the above picture that the table resembles two matrices of different orders. Now if we perform matrix multiplication on the above matrices, we get back the initial system of linear equations. Again, if we just end up performing matrix multiplication and equate it to the right hand side, we get the system of linear equations back. Now we'll go through some of the applications of matrix algebra and linear equations. Matrix methods are extensively used in solving complicated electrical circuits, in the calculation of battery power outputs, resistor conversion of electrical energy into another useful energy. These matrices play a major role in calculations. So we have an electrical circuit which has different elements. We have resistor, we have voltage source, and the direction of the currents can be represented with the following arrows. And now matrix is comes very handy in here. So let us try to see what matrix can do here. So applying Kirchhoff's current law in node 1, we can see that I1, this is node 1, so if we apply Kirchhoff's current law, we can see that I1 is equal to I2 plus I3. So current is nothing but voltage by resistance. So if we try to get in terms of voltage, we have this equation. Again, applying Kirchhoff's current law at node 2 of the above circuit. Node 2 is right here. So we can see that I3 plus I4 is equal to I1 plus I6. So again, forming this equation in the form of voltages, we have these equations. Now, solving for V1 and V2, we have this matrix. So below is the code for MATLAB in command prompt to solve for V1 and V2. So if we just give the values in MATLAB, MATLAB is a software platform where you can solve matrices easily and perform other calculations. So if we just end up giving values like this, we get the values of voltage. Now another example of matrix representation is the buck converter modeling. Buck converter is a DC to DC step down converter. It steps down the input voltage to a lesser value of the output voltage. So let us take this example and look at it. So it has two states. One is the state in which the position is on, and the other is the position. Other is the switch. Other is the position in which the switch is off. So we have different circuits for on position and one more different circuit for off position. Let us look at the on state. So from the on states, the state space representation can be determined as follows. During the off state, the state space representation is as follows. Summarizing the voltage mode controlled buck converter matrix, we have the equations. We have the matrix form equation state space representation as follows. Some of the other applications of matrix algebra in real life are in computer-based applications. Matrices play a significant role in the projection of 3D image onto a 2D screen, creating the realistic seeming motions. So this is the eye point of a human eye, if you can see, and this is a 2D plane having the x and y axis. So this is a two-dimensional plane, and this is 3D object. From the point of view of the humans, as we can see, the 3D object can be projected onto a 2D screen like this. One of the most important usages of matrices in computer-side applications are encryption of message codes. Here is the example of an encryption of message codes. So we have this plain text containing matrices of the order 5 by 5, and then we have the encryption key containing only binary values, that is 0 and 1. With the help of encryption key, plain text is multiplied with encryption key to get the ciphertext. In geology, matrices are used for taking seismic surveys. So seismic surveys, in this we have this matrix of the order of some order, and we can see there are certain different parameters which have to be related to certain different technical and scientific values. So these can be related in the form of a matrix. So wherever they have to be related, uh, they are just marked as dot so that they can be related as follows, and wherever there's no relation between them, it is left as blank. So this is a very integral part of seismic surveys. Seismic surveys have large number of matrices of large orders. At the end, this video was created as part of the requirements for the course EC 6325 State Space Control Systems under the supervision of Dr. Rose T. Fuggy at the University of Houston. Special thanks to Dr. Kaushik Rajshekhara, from whose slides figure X was taken, PowerPoint template taken from University of Houston website, other images and information courtesy of Wikipedia Google. Thank you.